Sorry, my computer restarted and it stopped the video, so I had to start it over again. If I wanted to finish creating these 80% confidence intervals, I would just take each of these sample means and just add and subtract 5. The answer to this one would be 32.2 to 42.2. And then the answer to this one would be 35 to 45, because 40 minus 5 is 35. 40 plus 5 is 45. I'll clear off some of this since I'm not using it anymore. So this one is actually 32.2 to 42.2 after adding and subtracting 5. So I actually made a mistake down here. This should be 32.2. And this one should be 42.2. I'll finish all of these. This one is 35 to 45. This is 37.5 to 47.5. Looks like this one is the same, because, well, both of them we're adding and subtracting 5 using 42.5, which gives us the same answers. This one will be 40 to 50, and this last one will be 42.5 to 52.5. So that finishes question number 4. Question number 6 is asking us to create a 60% confidence interval for each sample. So I'll make a label here that says 60% confidence interval. And then what makes it a 60% confidence interval is the fact that we're going to be adding and subtracting the 60% margin of error, which came out to 2.5. So let's take 32.5 and then add and subtract 2. No, I'm sorry, add and subtract 2.5. So this number that we're adding and subtracting is the 60% margin of error. The fact that it's the 60% margin of error is actually what makes our answer a 60% confidence interval. So when we subtract, we get 30. When we add, we get 35. So this first one is 30 to 35. Now what about for sample 2? We take the mean of sample 2, 35, add and subtract the 60% margin of error again, which is 2.5, and we get another 60% confidence interval. This comes out to 32.5, and this one comes out to 37.5. So that is the next one. What about for sample 3? Now we're going to add and subtract 2.5 again, this time using 37.2. Each time it's just the sample mean minus and plus the margin of error. This should be 37.5 minus 2.5. Sorry, not 37.5. 37.2, because that's the mean of sample 3. It's always the mean of the sample plus or minus the margin of error. This one comes out to 35 when you subtract. I think, actually no, because when you subtract 37.2 by 2.5, you get 34.7. And when you add, you get 39.7. $34.7 to 39.7. And when you do this one, you take the sample mean and you subtract 2 and you add 2. You subtract by 2.5 and you add 2.5 just like we've been doing. 40 minus 2.5 comes out to 37.5. 40 plus 2.5 comes out to 42.5. So that's our next answer. Next time we take the mean of our next sample, which was 37.5, add and subtract 2.5. 37.5 minus 2.5 is 35, and 37.5 plus 2.5 is 40. Now what about here? Well, the mean of this sample is 40. We subtract it by 2.5. 40 minus 2.5 is 37.5. Then we add 40 plus 2.5 and we get 42.5. So you just have to do this all the way across. So you'll have 1, 2, 3, 4 more answers for the 60% confidence intervals. The next question asks, well, I'll just let you fill in the other 4 here, and I'll just move on to the next question. Were the 80% confidence intervals wider than the 60% confidence intervals? Well, the 80% confidence intervals are in the top row, and each one covers a span of 10 numbers, because 30 to 40 is 10 numbers. 35 to 45 is 10 numbers. What about 32.5 to 37.5? That's only a span of 5 numbers. Also, 35 to 40 is only a span of 5 numbers. So each of the 80% confidence intervals are a span of 10 numbers, and each 60% confidence interval down here in the second row is a span of 5 numbers. So 10 is wider than 5, so each of these intervals in the top row are wider than each of the intervals in the second row, so the answer is yes, the 80% confidence intervals are wider. The reason why they're wider is because when we created them, we were adding and subtracting a larger number. We were adding and subtracting 5. If you wanted to double check your answer, you could take these first 2 confidence intervals, the 80% and 60% intervals for sample 1, subtract 40 by 30, you'll get 10. Subtract 35.5 by 32.5, you'll get 5. So the fact that this comes out to 10 and this comes out to 5, when you subtract that way, that shows that this is wider than this. That's one way to prove that it's true. The next question says, what does the 80% confidence coefficient equal? In order to do this, first we have to mark off the middle 8 of the samples again, because 8 out of 10 is 80%. So once again, if you leave off the highest and the lowest, you get the middle 8, which is the middle 80% of the samples. And we have to focus on the highest sample in the middle 80%, meaning, which is pretty much always going to be sample 9 up here. Second to the highest one. So this one is at the upper boundary of the middle 8, or the middle 80%. What we do with this sample is we take its mean of 45, and we calculate a z-score using this sample mean of 45. So the 80% confidence coefficient is the z-score of the highest sample in the middle 8, which is just the z-score of this sample right here. How do we do that? Well, remember what the z-score formula is? Z is sample mean minus population mean over the population standard deviation divided by the square root of the sample size. You might be wondering, why is this a confidence coefficient and not just a z-score? Why does it have a special name? The reason why we're calling it a confidence coefficient is just because the sample mean right here is coming from the highest sample in the middle 80%. And when I say middle 80%, I really just mean the middle 8. That's the only reason why it's called the confidence coefficient, is because we're calculating it using the sample at the upper end of the middle 8. That's why it's called an 80% confidence coefficient. So we take 45, the sample mean that we have to use to get the confidence coefficient. We can't just calculate the confidence coefficient with any sample. It has to be this one at the upper end. 45 minus the population mean of 40, which was over here, over the population standard deviation, which I provide to you, was calculated with these 5 numbers over here. Over the square root of our sample size. What's our sample size? Well, each of our samples had 2 people. It's 1 and 2. This is 1 and 2. This is 1 and 2. So each of the 10 samples has 2 people. So it's a sample size of 2. Remember, these numbers weren't there at the beginning. We calculated these. So we need to calculate this. The square root of 2 is 1.41. So it's 45 minus 40 over 7.07 over 1.41. That's what the square root. That's about what the square root of 2 equals. Next, we can just divide on the bottom, because instead of having a square root, we just have a number now. 7.07 divided by 1.41 is about 5.01, which means we have 45 minus 40 over 5.01. I'm running out of space, so I'm going to have to continue this up here. So when we divide this by this, we get about 5.01. Now we have to take care of the top of the fraction. 45 minus 40 is 5. We have 5 over 5.01. And 5 divided by 5.01. Just divide the top by the bottom. We get 0.998, which is about just 1. So the 80% confidence coefficient is 0.998. The next one says, what is a 60% confidence coefficient equal? 60% confidence coefficient will just be a z-score, but if the sample mean comes from the highest sample of the middle 6, it becomes a 60% confidence coefficient instead of an 80% confidence coefficient. So last time, the sample mean came from the highest sample in the middle 8, which was this one right here. That's what made it an 80% confidence coefficient. Now we want the highest one in the middle 6, which is, remember, the middle 6 are everything except the lowest 2 and the highest 2. So the middle 6 ends at 42.5. And since it ends at 42.5, that's what we take. So it's the sample mean at the upper end of the middle 6 minus the population mean. It's the same formula, over the same population standard deviation, which I gave to you. Sample size is still 2 because each of these samples is still 2 numbers. The bottom of the fraction will still come out to 5.01 because nothing has changed on the bottom of the fraction. So you could just skip straight to 5.01. Just put 42.5 minus 40 over 5.01. When you subtract 42.5 by 40, you get 2.5 over 5.01, which equals 2.5 divided by 5.01 is 4.99. I mean 0.499. The reason why I didn't do all of the work this time is because if this on the bottom of the fraction is what we had on the bottom of the fraction last time, there's no point in doing that math over again. We already know it equals 5.01. So our final answer when we finish using the z formula is 0.499, about 0.5. Now that we have these two answers for 7 and 8, we can actually use them to answer 9 and 10. Now, how do we calculate an 80% margin of error using a formula? We knew how to get the 80% margin of error by just marking off this sample and subtracting 45 by 40. But how do we actually do it using a formula? Well, we can do it this way. To get the 80% margin of error, you multiply the 80% confidence coefficient, which we found in question 7. I'll put 80% CC for confidence coefficient times the population standard deviation, which I gave to you in this question, over the square root of your sample size. We have our 80% confidence coefficient from question 7. We can just plug that in right here. We know what the population standard deviation equals. I gave it to you, 7.07. Our sample size is still 2 because each of the 10 samples has 2 numbers. We can take care of the square root first. We know that the square root of 2 is about 1.41. So it's 7.07 divided by 1.41. We still have 0.998 in front. Remember that if you have something outside of the parentheses, it means multiply. So even though we don't have the multiplication sign anymore, it means it still means this times all of this. So now that we've answered the square root, the next step should be dividing inside of the parentheses, which is just this number divided by this number. 7.07 divided by 1.41, which is 5.01. So now, inside of the parentheses, all we have is 5.01. Now let's multiply, because all this is saying is this number times this number. 0.998 times 5.01 is 4.999, which is pretty much just 5. It rounds off to 5, so we get the same answer that we had before. We just calculated the 80% margin of error using a different method. Now what about the 60% margin of error in question number 10? This is a very similar, this is going to look very similar to what we did last time. Just instead of it being the 80% confidence coefficient, it's the 60% confidence coefficient times the same thing right here. So if we multiply 60% confidence coefficient by the population standard deviation over the square root of our sample size, it's just going to be, well, the 60% confidence coefficient was 0.499, so we just plug that number in. This doesn't change because it's still the same numbers, so just plug those same numbers in over again. Only the confidence coefficient changes. And we know that this is 1.41. So it's 7.07 over 1.41. We divide this number by this number inside of the parentheses. We get 5.01 again. And then 0.499 times this number inside the parentheses. just multiply this, and we get our answer. Times 5.01 is, no, that can't be right. Let me do this again. 0.499 times 5.01 is 2.499, which is just 2.5 when you round. So we found the 60% margin of error, and it matched the same answer we got last time. So all we did was just use a new way of finding the same answer we had before. So this is 5. This is 5. This is 2.5. I want you to show your steps for these questions so that I know that you just didn't just write these two numbers over again. Let's see. I'll show you how to do the next part, which is in class activity part 2. It looks like this. What about, it says p-value. The definition of the p-value is the probability of getting a certain outcome or an outcome even further from 0 when the null hypothesis is true. So, well, the definition of the p-value is a little bit wordy and complicated, but it's actually not that hard to calculate. What we do is we put this over here, and we put this over here. That's our first step. So what I want you to do is just take this first one up here and this first one down here and just copy them like this. Now what you do for the next one is, for this answer right here, is you mark off this right here and mark off this right here. And what I want you to do is add all of the ones that have that are either up here or down here. So, like, you see how we have, it's like we have two numbers that are above this line right here, and we have two numbers that are below this line down here. Add all four of them and see what we get. 0.011 plus 0.084 plus 0.084 plus 0.011 equals 0.19. What I did to get this is I added all four of them, and I got 0.19. And actually, we add To get this answer down here, you do the same step. You add all four of them, and you get 0.19 again. So we have this right here, and we have this right here. What you do is you add all of the numbers that are, well, let's talk about this one right here. You go right here, go straight across, and then find, take all of the numbers that include this number and above up here, and then also take the opposite and take this number and this number down here and add all four of them. What do we do next? We move this up higher. Now we have three numbers up here, 1, 2, 3, and we have three numbers down here, 1, 2, 3. We actually need to add all six of them this time. And after we add all six of them, we get an answer here and here. So let's do that. This one is actually going to be 0.011. Actually, let's start here. 0.24 plus 0.084 plus 0.011 plus all of this over again because we have to include the bottom three. And all of this equals 0.66. Should come out to about 0.66. Or maybe if you round, it might be 0.67. For this one right here, we do the same math over again. We get 0.67 again. So these ones in the p-value column are both 0.67. And what you might be noticing is when see how these two numbers in this column are the same? They're both 0.084. They both have the same answer over here. These ones that both say 0.24, so they're the same number, and they both have the same answer over here. So both 0.24s have the same answer of 0.67. Both 0.084s have the same answer of 0.19. And what about this last one right here? Well, notice how this was moving up and this was moving down. So instead of it just being this, well, pretty much what you do now is you just add all 7 numbers. So it's like this moves up and this moves down, and the 0.34 is included. So now for this middle one, add all 7 numbers. So it's 0.34 plus all of this. It's all 7 numbers. And it should come out to 1. Let's think about what we did. For the highest and lowest answers right here, we didn't add anything. We just took this and put it over here. We took this and we put it over here. For this answer and for this answer, we added the bottom 4 and the top 4. We added this plus this plus this plus this, and that gave us both of these answers. What we did for our next 2 answers, which was here and here, is we added the top 3 and the bottom 3. So we were adding 6 numbers. So here we added the bottom 2 and top 2. Here we did the same thing. Here we added the bottom 3 and the top 3. Here we did the same thing. And here we added all 7 numbers. So this one came out to 1, so our answer would just be 1 right here. After we filled in this column, we can now answer questions 1, 2, and 3. Getting all of these numbers is actually what we had to do first before we could even start answering these 3 questions. So what outcomes would lead you to conclude that there's too many red cards in the deck? And what outcomes would lead you to conclude that there's too many black cards in the deck? Notice how the p-value here starts at 1 in the center when you have 3 red and 3 black. And then the further you get from that, meaning the more imbalanced it gets in this direction, when red starts to take over, the p-value gets lower and lower. Down here, when the hand of 6 cards starts to get more black and fewer reds, the p-value also drops. Once going in this direction, once it drops to the point where it's less than 0.05, is when you actually say that there's too many red cards in the deck. Going in this direction, once it drops down to the point where it's 0.05 or less, you say that there's too many black cards in the deck. Or that's at least what you conclude. So let's see. Going in this direction, it starts at 1, it drops again, and this right up here is when it gets to be under 0.05, because 0.19 is above 0.05, but once you get up here, it actually does drop below 0.05. So that's when we would say, once it drops that low, we would say there's too many. Let me move all of this. Now let's go in the other direction. It starts at 1, it drops, and it drops again. Once I get down here, it's actually gone below 0.05. Here it was above 0.05. This 0.19 is above 0.05, but here it's actually dropped below 0.05. Once it gets to this point where it's under 0.05, we make the conclusion there's too many black cards in the deck. The reason, so whichever outcomes have a p-value under 0.05 lead you to conclude that there's something wrong with the deck. Up here at the top, where we have a lot of red cards and not many black cards, we conclude that there's too many red cards. Down here, where there's a lot of black cards and not very many reds, we conclude that there's too many black cards in the deck. And for everything in between, we make a different conclusion. All of these p-values are above 0.05. What you conclude for these is that there doesn't appear to be anything wrong with the deck. So you can even write it out this way. So what was the reason why we made this conclusion up here? Well, it was because P was under 0.05. What about here? We made this conclusion because P was under 0.05. And here we made this conclusion for all of these because there didn't, each of these would all lead to the same conclusion right here because all of these are above 0.05. Notice how when we go up here, we're getting more and more evidence that there seems to be too many red cards in the deck. But it's not till we get to this point up here where P is under 0.05 where it's actually convincing enough to make that conclusion. Going in this opposite direction, we're getting more and more black cards and fewer red cards, which means the outcomes are starting to show more evidence for too many black cards in the deck. But it isn't till the point where the p-value goes under 0.05 that conclusion is actually made down here. And all of these in the middle that have p-values above 0.05, all of those outcomes are less unusual. I mean, they're closer to being, well, they're closer to just being balanced between red and black. They're not as extreme or unusual. So all of these lead to the conclusion that there doesn't seem to be anything wrong with the deck. And all that really matters is whether the P is under 0.05. So you could even write the answers out this way. Just, you don't have to put these boxes around the numbers. You can just write your conclusions like this. And then you could make an arrow like this so that you don't have to write this answer every time for all of these. Let's now look at the third page. I'm asking 20 SJSU students how many hours they study each week and how many hours they spend working each week. This question asks for p-values. In this type of question, you don't actually calculate p-values. They're already calculated for us, and we can just get them from a table. So I'll show you what table to go to. I'll give you this table during the test. You can even bring your own copy if you want to. See right here, what it's telling us is that these rows in the table are actually n minus 2, which means the number of people that are being studied minus 2, which means if I tell you that there's 20 SJSU students, you just take this number and subtract it by 2 to get your row number. Is number of people minus 2, or sample size minus 2. If I tell you that there's 20 people, subtract it by 2, and that's your row number. Our row number comes out to 18. If I gave you 15 right here, you would subtract that by 2, and then the row would be 13. If I told you 25 right here, you would subtract 25 by 2, and your row would be 23. It just turns out that when, in this case, I tell you 20 SJSU students, and 20 minus 2 comes out to 18. So the row number is 18. It won't always be 18 because it depends on what number I give you here. Let's go down to row 18. See how we have a 0.10 column, a 0.05 column, a 0.02 column, and a 0.01 column? Those will be your answers. So for 0.10, up here in the first column, your answer is 0.7378. Now what about down here for 0.05? Well, we go to the 0.05 column and we get 0.444. That's our answer. Then 516 and 561. So once you know what row number to use, you can go to that row, and then your answer for 0.10 comes from the 0.10 column. Your answer for 0.05 comes from the 0.05 column. your answer for 0.02 is from the 0.02 column. It just works that way. Now what do we do here when we get to these questions about what conclusion should be made? The rule is to use this number here. So take your answer from question 2, which is the answer for p-value of 0.05. It'll always be the second one right here. Put it on a number line. Put 0 in the middle. Put the 0.44 up here. 444. In the question you do on the exam, it might not be 0.444 that you actually use, because if I give you a different number in the question, you'll end up using a different row, and then these numbers won't be the same. But even if it's not 0.444, it'll still be your answer to question 2 right here, whatever number you end up putting in here. Then, okay, so put that number here, and then also put its opposite right here, which would be negative 0.444. Just take this and put a negative sign in front of it, and then put it down here. Now, we're going to make 3 different sections on this number line. Conclude that there doesn't appear to be any correlation in the population. That's the middle area. The upper area so we have 3 sections of this number line. Each one leads to a different conclusion. Okay. I might want to extend this out just so you can see that it's still a part of the number line. We need to take this 0.2. Actually, this should be negative 0.25, and this should be negative 0.59. We need to see where each of these fall on this number line. Once we find out which area it falls into, we make our conclusion. So, negative 25, 25 is in this middle area, because one way you can figure that out is look at this right here. Look at these first 2 digits. It's a negative 0.44, which is 44. 25 is smaller. 25 is smaller than 44, which means it's closer to 0. So negative 0.25 falls in here. Since it falls in the middle area, we conclude there doesn't appear to be any correlation in the population, meaning in this case the San Jose State population. So you can put your answer right here. What about 0.25? Positive 0.25. Well, that falls in the middle area also, because if you look at this, at the first two digits right here, after the decimal point, it's 44. 25 is smaller than 44, which means 0.25 is closer to 0. So it also falls in this middle area, which means since it's in the same area between these two numbers, since it's still between this negative number and this positive number out here, it's the same conclusion. We still make the conclusion that we make in the middle area. If it falls in the middle section, we make that conclusion. What about negative 0.59? That's actually out here somewhere. It's actually in this left area. Remember, these are the cutoff points. So the middle area was in here. The left area is out here. Since negative 0.59 falls in this left area, we conclude that there's a negative correlation in our population. Now what about, well, first let's think about why is negative 0.59 out here. Well, 0.59 is bigger than 0.44, which means that 0.59 is further out from 0, out this way. So that's why it is beyond this red cutoff point. What about 0.67? Well, 67 is bigger than 44, which means that 67 is further from 0. So it's out here past this red. It's out past this red line. So it's maybe out here somewhere. So it falls in the right section of our number line. We have a left section, a middle section, and a right section. It falls in the right section out here, which means we conclude that there appears to be a positive correlation in the population. This one should have actually said there appears to be a negative correlation in the population. That's just the wording, a little bit of wording that I left out. So since it falls in this right section out here, conclude that there appears to be a positive correlation in the population. That's the third answer. So this is how you would answer all four of these. Somewhere on the exam, I'll tell you what the wording should be for each of these three sections. So these are the four answers. We just had, for each of these numbers, we just had to look at what section it fell into. If it fell in the left section, we had one answer. We had this answer. If it fell in the middle section, we had this answer. If it fell in the right section, we had this answer. But before we could actually answer these questions, we had to know what our cutoff points were. So we had to take this answer here in the circle, which went along with this 0.05 right here. We took this number, we marked it off up here. We marked off the opposite down here with a negative sign in front of it. And these were the two cutoff points. Once we put these on the number line, we had our three sections. And then we could actually answer these questions. And when you put your cutoff points here, make sure to always use your answer to question 2, which is where it says 0.05. Don't use any of the other three.